Hey, you guys, here's your first installment in chapter 10. We're talking about chemical bonding. We're continuing on chemical bonding. We kind of beat ionic bonding and covalent bonding to death in chapter 9 and Lewis structures, but now we're going to start learning about the shapes and the geometry of molecules and then hybridization as well in this chapter. In this first installment video of the PowerPoint slides for chapter 10, we're going to be doing sections 1 through 3. So let's talk about VSEPR, or valence shell electron pair repulsion model. This is a model that talks about how the shape of a molecule is dictated by the repulsion of the valence electrons that form the bonds. So what we're going to do is we're going to go through a table. We're going to look at a class. This is called the Vesper class over here. And that Vesper class, VSEPR, consists of a certain code, and we'll see what that code is right now. So if we look at our first class, AB2, this A is the central atom, B is the surrounding atoms. That means that this molecule only consists of a central atom and 2 surrounding atoms. So the number of atoms bonded to the central atom would be 2, number of lone pairs would be 0, the arrangement would have to be linear. And that's because these electrons want to get as far away from each other as they can. The arrangement of the electron pairs is linear. Now, what gets confusing is that the electron pairs and the molecular geometry can sometimes be the same thing and sometimes different. In this case, they are the same because the number of electron pairs is 2 and the number of atoms is 2. So when you see the molecular geometry, it's asking you about atoms. If you see the electron pairs, it might be asking about any lone pairs that are also present. And here's an example of something that's linear that falls into the AB2 Vesper class, 180-degree angle. And so there's a little recap of the fact that there were 2 atoms and 0 lone pairs. Let's talk about the next class, which is AB3. The number of atoms bonded to the central atom is, of course, 3. The number of lone pairs is 0. The arrangement is trigonal planar for the electron pairs, and the arrangement for the molecule is trigonal planar because the atoms and the electron pairs are the same. And there's an example of a trigonal planar molecule. It is planar, meaning it's flat. So if I was going to try to draw this 3-dimensionally, I might think about making a line here to be one of them, and then this one may be coming out at me, and this wedge means to come out at me, and this, I'm going to make this guy a dash, means to go away, and then this would be in the plane of the paper. So if I was trying to draw this and then put some atoms around here, then this is what it would look like. Now, and these angles are 120. The reason this angle looks larger is because I was trying to give it perspective. Now let's talk about the next class, which is AB4. AB4, number of atoms for that one is 4, 0 lone pairs, and this guy is called tetrahedral. That's 4 things around an atom, and if it's 4 atoms, then the molecular geometry is also tetrahedral. And there's an example of a tetrahedral molecule. Methane is very common as an example for this, and there is that wedge that I was trying to show you, and what I could do is make this guy a dash, and that shows it going away. Let's do the next one, which is AB5. AB5 has 5 atoms, 0 lone pairs. The arrangement for 5 atoms around a central atom is trigonal bipyramidal or bipyramidal, however you'd like to say it. To dissect this shape a little bit further, you'll see that we've got 2 sets of angles. We have angles that are 120, and then we have angles that are 90. The 90-degree angles are between the top and the bottom positions. These top and bottom positions are called axial positions. And then the angle between the equatorial positions, which is what these are 120. The angle between the axials like this is 180. The trigonal bipyramidal structure would also show up for molecular geometry if they were all atoms. An example of this is phosphorus pentachloride. Now this guy has an expanded octet. You can see he has 10 electrons around the central atom. And if I want to play around with some sort of geometry showing here, I might do that type of thing. That is a wedge, and that is a dash. And then these are in the plane of the paper. These are the equatorial positions here. And then these are the axial positions here. Let's go on to our next. AB6, six atoms bonded to the central atom, 0 lone pairs. The arrangement for this is called octahedral. And if you take a peek at this structure, the reason it's called octahedral is because all the angles are 90 between them, as well as if you colored this in, you would see that this shape here is called an octahedron. And that's where, so the octa comes from 8, which means 8 faces. There's 4 faces on the top, 4 faces on the bottom. And if they're all atoms, then of course the molecular geometry would also be octahedral. An example of this is sulfur hexafluoride. You can see all the different angles are 90 degrees. So they're not different, they're the same. And here is an example of a dash wedge line structure. The only ones that you would put dashes and wedges, this is going away from me, and this was coming towards me. These guys up here and to the side here are in the plane of the paper. So this is a table in your textbook that just reviews everything we just did. And when you're doing fun sheet number 1, this is what you might want to look at to get how to draw these and put them in your fun sheet. Let's talk about some examples of these as far as looking at different ways to put these things together. This one, Vesper class, would be AB4. Now we're jumping ahead a little bit. This Vesper class we haven't covered yet, but it's it wasn't in that table a second ago, but this is AB3E. And this E stands for the lone electron pair right up here. It still has 4 things around it. And since it has 4 things around the central atom, this arrangement of all 4 is tetrahedral. Now the angles of that tetrahedralness start to change when you have lone pairs involved. And that is because the lone pairs take up more room. So they actually press down on these, compressing this angle as much as possible. This happens also in water. The Vesper class for this one would be AB2E2, and that is still 4 things around that oxygen. So you have a variation of the tetrahedral angle here. These guys these lone electron pairs are taking up more space, so this would definitely be squished. But these are all tetrahedral arrangements around the central atom, but some happen to be electrons and some happen to be atoms. And you can see up here in this top, I think they're trying to illustrate that these lone pairs take up much more space. So when we're looking at the repulsion and how it changes the shape, lone pair repulsion is larger than lone pair bonding pair repulsion, and then even bigger than the bonding pair. And that affects your angles that you see in the molecule itself. And there's the angles that we were just discussing. Let's keep on going with our Vesper class. Here we have, this is going to be like derivations of the main Vesper classes. A Vesper class of AB3 was trigonal planar, if you recall, if you had 3 atoms here. So now if you put in a lone pair with it, we get AB2E. That's 2 atoms and 1 lone pair. And now your shape becomes trigonal planar of all the electron pairs, but of the molecules alone, it becomes bent. AB4, on the other hand, now let's keep on going. We're just going to increase the number of substituents or groups around the central atom. Before we saw 4 for our straight tetrahedral arrangement for electron pairs and molecular geometry. Remember, they were the same if they were all atoms, like they are in this case. But let's put an electron pair, and that's what we were seeing on that previous slide. 3 atoms, 1 electron pair, lone electron pair. All of them together would be tetrahedral, but since 1 is a lone pair, it pushes these down, and then you have what's called a trigonal pyramidal structure. And there's your lone pair in the ammonia molecule. Now we can put 2 lone pairs, and if you remember, water was our example on that previous slide. 2 atoms, 2 lone pairs, overall tetrahedralness, and then it becomes bent. And the reason it's bent is because we are just looking at the atoms themselves, and that's the atoms. There's the bentness. Let's go to our next Vesper class, main Vesper class of AB5. When we had 5 atoms and 0 pairs, we had a trigonal bipyramidal structure for both of them. If I put 1 lone electron pair, we're at 4 and 1, and our new shape is called distorted tetrahedron. This is piggybacking off of the fact that this whole thing is trigonal bipyramidal, but one of them is a lone pair. So it squishes these down and it pushes them this way, and it's called a distorted tetrahedron. And that distorted tetrahedron has different angles. And you can see the angles that they would have normally been are now compressed. Let's try the next one, which is AB3E2. 3 atoms, 2 lone pairs. Again, our overall shape is still trigonal bipyramidal because it's 5 things or groups around that central atom. But now our shape becomes what's called T-shaped. Now, if you look at this example here, it looks like these angles are still 90, but they're not. These actually over here become less than 90. So if you were asked about angles like you are in your fun sheet and it was a T-shape, you would say less than 90, not 90. Both of these are taking up a lot more space. Let's go on to another example, which is still 5 things around, but now 2 atoms and 3 lone pairs. Again, still trigonal bipyramidal, but now our new shape is linear. So a common example of this is called the triiodide anion, and you can see that these lone pairs, now I want you to remember that lone pairs in this trigonal bipyramidal take the equatorial position. The reason they take the equatorial position is because there's more space around there. They're not so close to those 90-degree angles. So lone pairs go in the equatorial positions, and then the atoms take the other positions. Let's go to our last VSEPR class, which is AB6, and the derivations we're going to see. Octahedral is the arrangement of the electron pairs. But if we put one of them as a lone pair, the main shape is still octahedral for everybody, but now when one is a lone pair, it becomes square pyramidal. Now, I said I have on here, see table 10.2. It has all of these. It has all of the structures that we've been looking at. Let's do another one. AB4E2 is an octahedral takeoff here. 4 and 2. 4 plus 2 is 6, so we're still octahedral overall. But now the lone pairs are taking opposite locations here because they take up more room, so they're as further away from each other. Now we're just looking at the shape of the atoms, and that becomes square planar. So the square planar, it's in a plane, which is all in one flat surface, and it's in a square shape. So on your fun sheet, and what you'll be doing there is to just go over this and look at the different types of drawings that we could do. Now, what I wanted you to do and how it helps me understand things is the goal is to draw one of these things three-dimensionally. Three-dimensionally means, now this one, there's a couple ways. This would be trigonal planar. So you could draw, if I had A in the middle like this, I might draw one going back, and then one going to the side, and then one coming out in a dash wedge line structure, because it's trigonal planar. Now this site right here is a PhET site, and it's nice to go there and build your own molecules, look at the ideal bond angles, and sketch what you see there. There's also a neat little add-in called Chem for Word. And if it's an add-in in Microsoft Word that enables you to draw Lewis structures, it's quite handy, and it does a great job. So if you were to click on that site, you can go to a PhET site, and it looks a lot like this. And when you build a molecule, you can choose a central atom like they have done here, and it's purple, so that this is always here actually. And then you run over to here, and when you tap on one of these, this will take that away. If I hit this X, one of these would disappear. But if I hit this, one would show up. So I can keep on building things. I can build things with double bonds or triple bonds, or with all single bonds. I can even put lone pairs on the central atom. So what you can also do is show bond angles, and that gives you an idea of what the bond angles are, because remember, you're going to do that over here. And then if you look right down here, if you have both of these checked, it will give you what the molecular geometry is, as well as the electron geometry, which is what we were covering before. So this is a great way to check your work and see if you understand how to draw and know the bond angles for these different molecular shapes. But how do we predict molecular geometry? To predict molecular geometry, first and foremost, you probably have to know the Lewis structure. The Lewis structure tells you the number of atoms surrounding an atom, as well as if there's lone pairs or lone electron pairs present. So how to do this? We count the number of lone pairs on the central atom and number of atoms bonded to the central atom. We're going to use VSEPR to guide the geometry of the molecule. So let's do an example. What are the molecular geometries of SO2 and SF4? Well, we have to know the Lewis structure. So once you draw the Lewis structure and you feel comfortable and confident that you got it right, you look at the atom that you're trying to determine the shape around. So this guy is our central atom. And to determine the shape around that one, we count the number of lone pairs and the number of atoms. So it looks like we've got one lone pair and then 2 atoms. That makes 3. And the VSEPR class that this is going to be would be AB2E. So if you recall, this guy is bent. So for SF4, so if I was drawing this correctly, you might want to just draw it with your lone pair here and then actually show the bent structure right here. And so you might see this drawn like this in the literature because this is actually what it looks like. SF4, do the same thing. You would count your number of things surrounding the sulfur. And I want you to keep that in mind when I say count the number of things, we're going to do that hybridization also. So we want to just know how to do that when we come later in this chapter. So in this example, you have 1, 2, 3, 4, 5 things. And when there's 5 things, and one of them is a lone pair, 4 of them are atoms, it's AB4E. And if you recall, the shape for that would be distorted tetrahedron. So what is now that we know how to draw the shapes of these things, and the shapes are going to help us understand some molecular properties like dipole moments and polar molecules. We've already done this just a little bit in chapter 9 fun sheet. I jumped ahead a little bit and said, what's a polar molecule? And I gave you guys a video that I thought was pretty good. But as far as dipole moments and polar molecules, a dipole moment is a difference in charge. And a dipole moment, it's 2 poles, and it has a partial positive end and a partial negative end to it, to the whole molecule. So in the example you're seeing here, this is hydrogen fluoride gas, and you have a dipole moment that is also the same as the bond moment. So this, I had you guys in chapter 9, I had you draw bond moments. A bond moment is showing the differences in electronegativities between the atoms. So now we know that fluorine is more electronegative than hydrogen, so he's going to draw the electrons in the covalent bond towards himself, and then it's going to make this end of the molecule negative, and this end of the molecule partial. It stands for partial negative and partial positive. So a dipole moment is given this little symbol mu, and this little symbol, I think I have that right. Yeah, that's like micrometers. And then this is Q times R, where Q is the differences in charge, and R is the distance between them. So this is measured in what's called a debye, and that's a funny unit, but it's named after a person, D-E-B-E-Y-E. And it's a unit that is for this exact thing, which is the charge times the distance. And this is pretty small, and it's a coulomb meter. A coulomb is a measure of charge, a meter is a measure of distance, so that's all there is to it. So this was in coulombs, and this one is in meters. So when we have a molecule like that, if it was floating around in a container, say this was closed, and I was able to magnetize or put an electric field on, if it was a dipole moment, you would see them all line up positive to negative. If this was the positive side and that's the negative, you'll notice the positives are towards the negatives and the negative is towards the positive. That's an experimental evidence that a molecule is polar. So in your book, you see a little example here of table 10.3 that shows different molecules and their dipole moments. Now, if you check out these numbers over here, you'll notice the larger dipole moments belong to compounds that have elements in them with large electronegativities. So fluorine here has a large electronegativity, and water has, oxygen has a large electronegativity. So you'll get larger numbers here. So when we look at drawing bond moments that then give a dipole moment, and I ask you guys to do this on your fun sheet, is the bond moments, you see here I'm drawing in red, they all add up to make the overall dipole moment that you see up here in green. So all of these are adding up. And the nitrogen, it's the same thing over here, nitrogen to fluorine, but you'll notice in between hydrogen and nitrogen, nitrogen was more electronegative, so the bond moment pointed towards the nitrogen. In the nitrogen trifluoride over here, the fluorine is more electronegative than nitrogen, so the arrows have switched themselves. So now they're all pointing in the direction towards the fluorines, and they all add up to make the overall dipole moment point down here. So when you look at this molecule, the bottom of it has a partial negative and the top has a partial positive, kind of. I mean, you see it's, but you see how big these are. This means much more negativity down here. And then over on this one, you'll see you got a partial negative at the top and a partial positive at the bottom. So if you were to put this in an electric field and turned it on, the positive and the negative, you would see this guy flip, and this would go towards the positive, and this guy would go towards the negative. So for this one, we say, which of the following molecules have a dipole moment? Well, what do you have to do in order to figure this out? You have to draw the Lewis structures. So when you draw those Lewis structures, you can then put in the bond moments, and then that will give you an idea of the overall dipole moment. So there's your bond moments, and there's your dipole moment for water. Now this is kind of not a great way of drawing it, but this is a bent structure, and it's bent because of the lone pairs. Putting it down here makes it a little deceiving, but either way, even if you were to draw it like it really is, and you have hydrogens like this, and then you have oxygens up here kind of in their lone pairness, then those bond moments you see point that way, and they both add up to give the overall dipole moment like this, which is what that's showing in that little animation there. Okay, so for carbon dioxide, those bond moments cancel each other. And since they cancel each other, there's no dipole moment. It's a nonpolar molecule. So if you put this in a field, I know it seems weird because you think, oh, well, this should be partial positive. And it is. This carbon is partial positive, and the oxygens are partial negative. But since they point away from each other, these vector quantities cancel each other. And experimental evidence shows when you put it in a field and you turn on the field, nothing happens. The carbon dioxide molecules do not respond. That means that these must cancel each other, and therefore the molecule must be nonpolar. Let's try sulfur dioxide. By looking at this and putting in your bond moments, you can see that they add up and you have an overall dipole moment, and so your sulfur dioxide is polar. Finally, carbon tetrafluoride. Put in your bond moments, and it doesn't look like it. It's a little harder to see in this one for me anyway, that these all do cancel each other, and it is a nonpolar molecule. So let's keep on going, just a little bit more practice here. If we were doing boron trifluoride, we would again put in the bond moments, and it looks like again that trigonal planar structure, they will cancel each other out and it will be nonpolar. And this little drawing here, this is called these are out of your textbook, and these are called electron density maps. And that electron density, where it's red is negative and where it's blue is positive. So this means that you can say, oh, look, it looks like it's got all these negative ends and then a positive in the middle. No, since they cancel each other out, there is a positive center, and that is true. And that positive center does attract negative things like electrons, and reactions will occur at that boron center because of it. But as far as being a polar molecule, those bond moments cancel each other out. So it's nonpolar. So let's try CH2Cl2. Does it have a dipole moment? Well, you can see in this picture it does, because we have two of the moments between hydrogen and carbon pointing towards the carbon, and these pointing towards the chlorines, and they all add up to make a resultant dipole moment. And again, you see some kind of more reddish on this side and more bluish on this side. So we got a partial positive on this part of the molecule and a partial negative. Recall that a dipole moment, or a dipole molecule that is a dipole, only has two poles. So you notice I have 1, 2 poles, and it reacts to an electric field. So for Funchy question number 3, what I've asked you to do is just, to practice this, is to go to a site, and I'm going to show you that here in a second. There's a site here that will help you and guide you through every one of these, and that you will be able to look at a molecule. You want to add up your total number of valence electrons so you can draw the Lewis structure. Now, I think in yours, I might have combined these, or maybe I think that was in the very last experiment. In the very last experiment, our molecular modeling experience, we will do this exact same table. And so we don't have to do it twice. And then what you're going to see here is in the inquiry manual, these are combined. So either way, to draw the 3D structure, I mentioned a chem for word, which is an add-in. I drew these things with Chem for Word, I think. Yeah, I did. I drew them in there, and they're very nice. You can add in the lone pairs, and then you can even add in and give some what's called three-dimensionality or stereochemistry is what it's called to these molecules. So your goal is to go to the site. You can do this part first if you want to, figure out the VSEPR class, and then figure out the electron arrangement, figure out the molecular geometry, and then going through what we were doing earlier, figure out whether the molecule is polar. Not each bond, you have to go through each bond, but you want to figure out if the molecule as a whole is polar, doing the same type of analysis that we did before. And then guess some bond angles. And when I say guess, you're going to have them based upon the ideal bond angles, and those ideal bond angles for tetrahedral, for example, were 109.5. But remember, when you have this lone pair over here, it makes them less than 109.5. So that's what you would list here. The site that I'm talking about looks like this. It looks like I chose XEF2, and then you'll get little screens that show up that are helping you through drawing the Lewis structure and understanding the shape at the end of the day. And I don't know if it does polar or non-polar. You'll have to check it out. Now, as far as this very first question it's asking you is about sigma bonding pairs. And sigma bonding pairs is an electron pair that's involved in a single bond right there. So in this example, you would say you have how many bonding pairs do you have? 2. And then for non-bonding pairs, now this is around the central atom, so they're talking about a xenon here. You have 3. And then you hit your check button. I always forget that. I want to hit continue. And it'll say you must check your work. So hit the check button, and if you get a green check like that, you continue, and it'll go to another question to help you through the table in your fun sheet. So we will have a discussion on this that will help you. If you have any questions, you want to post your work, and then we can go through it together. See you in the discussion board on that.